Okay, all right. Okay, everybody's favourite stats topic, hypotheses testing. It's actually where it starts to get good, but you might not agree. Right, so we're going to do some hypotheses testing for the mean of a normal distribution. And remember, when we're talking about the mean of a normal distribution, we're talking about the population mean. And we can actually sort of take samples from that population to decide whether or not it seems that the population mean is as it is. Because how do you find the mean of a population anyway, if your population is massive? I'll leave you to think about that. So the key thing here is that if you're in a normal distribution and you take lots and lots of samples of the same size from your normal distribution, then the distribution of the mean of those samples is also a normal distribution. And so you can perform a hypothesis testing on the mean of the sample to see whether or not the mean of the population looks realistic. You might have to rewind now and replay it. I think it came out right. So for a random sample of size n taken from a random variable x, which is normally distributed, population mean mu, variance, standard deviation squared, then the sample mean, so when you just notation, so we use sigma for population, for, oh God, I'm in the wrong thing. Right, we use mu for the population mean. And we do x with a bar on top for a sample mean. So when you're taking a sample from a population, then you do x with your bar on top. So the sample mean, x bar, is normally distributed, and the parameters, the mean stays the same, and the variance becomes the old variance over n. And so the standard deviation, and this is the mistake I make with these, the standard deviation is going to be equal to the standard deviation of the old one over the square root of n. So the standard deviation of the mean, you need to square root top and bottom of this fraction. So just be a little bit careful. That's really easy to miss that root on that n. I think that's it. Right, I'll go over a couple of examples from two different books, actually. I feel like making one up. And we can talk through both. So the first one, Anna believes carbon dioxide levels in Avonford have risen above the usual mean level of 328 parts per million. Previous research has shown carbon dioxide levels here to be normally distributed with a standard deviation of 2.5 parts. Where did I get millilitres from? Sorry. Can we just see if that's 2.5 parts per million? She collects a random sample of 10 specimens, so 326, 328, 330, 330, 331, 331, 332, 332, 334, 336. These are actually really nicely distributed, which would suggest they're normally distributed. They're very symmetrical. Use this data to test at a 0.1% significance level and as belief. Right, normally we do a 5% significance level in maths. Having this as being 0.1 is really tight. So if she finds out that actually we're going to accept the alternative, she can be like pretty sure she's made the correct decision because of that tight significance level. You're only going to make the wrong decision 0.1% of the time if you accept the alternative. But it does mean that sometimes you'll accept the null when you should have accepted the alternative. So that's the drawback of having it that tight. So you need to lay these out like the ones you did last year. And so we have a null hypothesis. and that is that the mean, and we're talking about the population mean, is 328. The alternative hypothesis is Anna's belief, and she thinks levels have risen. So she thinks the population mean is actually more than 328. I need to check an exam mark scheme, but I'm pretty sure you might have to define your parameter here. So where mu is mean level of carbon dioxide in Avonford. But we'll check that. I'll check that for you. And then you find the probability of being in the tail. So here's the normal distribution. We're actually doing the distribution of the means, but don't worry about that. The mean is still 328. And the one that she's got in her specimen is going to be all of these added together and divided by 10. That's the sample mean. So the sample mean comes out as being 331, which is over here on this distribution. And we want to find the probability of being in this tail. It's exactly like the binomial ones. You should find it slightly easier than the binomials, hopefully, having done them last year as well. So we want the probability of being in this tail of the distribution. It doesn't hurt to sketch it. So we want the probability that the mean of the sample is more than 331, but you need to use the normal distribution for the samples. So the sample is normally distributed with a mean of 328, and the variance is going to be 2.5 squared over 10. Like so. So that's what you're putting into your calculator. But I need my calculator. Right, here we go. So as normal, you go to option 7. I'm on normal CD again, so option 2. My lower bound is 331. My upper bound is big, 1,000 will do. Right, just be careful here. So standard deviation is 2.5 over root 10. So 2.5 divided by root 10, or put it in as a fraction if you prefer. And then the mean is 328. So in this distribution, the probability of getting a value of 331 or higher is very small. For some reason we don't use standard form much in maths, but you're welcome to use standard form. So it comes out as being 0.0000739, or 7.39 times 10 to the minus 5. As a percentage, I'm going to times that by 100. So it's a tiny probability of being in this tail. And the key thing is this probability is less than the significance level. So you're basically saying if the mean was 328, I have a 0.00739% chance of getting a mean of my sample of being 331, which is incredibly small. And the key thing is that it's smaller than the significance level. It's less likely to happen than the significance level. So we're just basically saying actually that's just too unlikely to happen by chance. And so the mean, there's enough evidence, I'm going to word this properly, to suggest the population mean is bigger than 328. And so for this one, we accept the alternative. And then you need to do a conclusion in words. So there is sufficient evidence. You never say it's right or wrong because you're just collecting evidence. You have a 0.00739% chance that you've made the wrong conclusion here and that you've accepted the alternative when you shouldn't have done. It's unlikely, but it's possible. So there is sufficient evidence to suggest the carbon dioxide levels in Avonford are rising. So I'll do another example on a lower tail, and we'll look at when you would accept the null rather than the alternative, just to kind of clear that up. If that feels awkward, just rewind it and replay it a million times so you get it, well, maybe not that many times, or tell me and I'll try and explain it differently. But hopefully that's okay. The key thing is the significance level. If it's less likely to have happened than the significance level, you accept the alternative because you're just saying that's too unlikely to have happened by chance in this distribution. So I'm going to go with the alternative hypothesis. And actually, I think the mean might be a little bit bigger than 328.